All right. Well, welcome everyone to the afternoon session. It's my pleasure to reintroduce Dr. Carlo Lipizzi from Stevens Institute of Technology. And this afternoon, he'll be talking on the research task WRT-1023, Analyzing and Assessing Contracts for Embedded Risk. And with that, I'll turn it over to you, Dr. Lipizzi.
Thank you, Tyler. Thanks a lot. Thank you for having me. So it's a pleasure to be here this afternoon talking about this project that we liked a lot, that was reusing some of the work that we did in another project that I presented this morning. My name is Carlo Lipizzi, working at the Stevens Institute of Technology and at the System Engineering Research Center. At Stevens, I'm managing two graduate programs, Systems Analytics Engineering Management, and within the School of Systems and Enterprises, I'm sort of a point of reference for data science in a broad sense. At CERC, I'm researching primarily on AI machine learning and natural language processing, stressing in particular the natural language processing aspects. And that's what we are going to talk about this afternoon with this project, WRT-1023, that we are developing with Defense Acquisition University, and it started about a year ago. So the title was Analyzing and Assessing Contracts for Embedded Risk. That is a very generic term. Basically, the goal is to help the contracting officers doing the job of classifying incoming requests for the most appropriate contract type. Contract types are a way to protect the risk of the DAU, the broad sense, in not having all the coverages that are required for the specific elements in the request. It was a challenging task that we divided in multiple phases, not necessarily distributed in the same number of years. So we developed the prototype that I will show you in a few minutes, starting from the normal way of doing systems, interviewing, talking with all the stakeholders. Ray Ward in particular, we are very grateful that he was on board. He helped us a lot. And based on the modus operandi of the contracting officers, the available literature, we wanted to recreate the process in an automatic way. The idea is, again, interviewing the contracting officers to get how they do what they do, and read the literature to create a logical framework. Then create a computational model, eventually a little bit of visualization, and then deliver a prototype that they can play with. It's a prototype, it's not a system, meaning the user interface may not be ergonomically great, it may crash, but it will be useful for them to understand what can be the potential use for the system, and for us to get the feedback and move on eventually with the next phase. We have been informed of the existence of 10 different contract types, some of them with a certain level of similarity. meaning that making the distinction between one and the other may not be that easy. The job of the contracting officer we are addressing, it's basically classify requests, acquisition requests by contract type. It's that simple. The point is, this classification is not black and white. It's not something that you can do with a rule-based system. What if you cannot do that? Because there are sort of more probabilistic approach to take into consideration. It's a combination. So at the very end, we've been forced to use a system that was more sophisticated than just a if-then approach. And that was one of the key points. We identified keywords that are the characteristics of each contract type, but there is no real combination of the keywords that can be enough to classify a document. Reality is that the classification is really rooted in the semantic analysis of the text. So even if at the very end it's an algorithm, but you need to give to the algorithm a connotation that is semantic. The semantic, in this case, is basically related to the knowledge of the contracting officers. The idea was basically to recreate somehow create a computational representation of the knowledge of the contracting officers. And then use that knowledge base for taking the decisions. It's a two-step process. So the first step is to create the corpus, the knowledge base, and the second is to create the computational representation of this knowledge base. We use for that what we call the room theory. I mentioned this approach during the presentation that I gave this morning on WRT-1023. The room theory is based on the framework theory that was developed by Marvin Minsky mid of the 70s. That is kind of represented by an example that he was used to give to explain the theory. So when you enter a room, you understand if the room it's a bedroom, a bathroom, a living room, or something else. Not because there is a label stating what it is, but because you have a mental framework that will enable you to classify what you see as a bedroom, a bathroom, or whatever. So this mental framework, it's the framework that Marvin Minsky was mentioning in his theory. In the 70s, there was no computational representation. I started working in AI in 1986, and Marvin Minsky, Noam Chomsky were leading names in NLP. But we didn't have that much of computational power. So we used to work in Lisp. Those machines were very expensive, difficult to find. So there was no way that we could create a theoretical a computational framework to this theory. So using vectorization, we transform the text creating the knowledge base into a matrix where the rows are the words, the unique words, where words can be single word or multiple words, like system engineering. And the columns are numbers defining that word. So we generally use 300, but I mean, it's a parameter. The standard is 200 or 300, let's say 300. Each word is represented by 300 numbers. So this entire matrix is basically positioning the words in the corpus in a 300 dimension space, meaning that you can see the proximity of the words based on the distance they have in this 300 dimensional space. So, because of the example used by Marvin Minsky, we renamed the whole theoretical framework as room theory. So that's the reason for the name. Because, I mean, it's based on a knowledge base. If you have a different corpus, you can create a different point of view. So you can analyze the same text as a contracting officer, or as a vendor, or as a technology expert, whatever. So that's the way it works. You basically have the room, that is this matrix, this n by 300, where n is the number of unique words matrix. And then you have the request that you want to evaluate, and the characteristics, the keywords defining the contract types. So you basically take each word of the request, and you compare with the keywords using the representation on both the sides of the word, the individual words in the request, and the individual keywords on the benchmark list, using the room for the lookup to get the vector. So once you have the vector, then you can define the distance, and you can, I mean, you add all the words, all the matching values with different contract keywords for each contract type, and then you define what is the closest, and then that will be the classification. So initially, we collected the information through existing contracts, existing requests, and we used a limited number of keywords. So we realized that that was not giving that much of a separation between the different contract types for the classifications. We asked the sponsor, what are the characteristics of the ideal contracting officer? Meaning, when you hire a contracting officer, what do you request? What is the background that they need to have? So is this law? It's MBA equivalent? So he gave us a list of skills that they need to have. We went back to getting textbooks, publications on those, just to physically recreate the knowledge that a contracting officer should have. So we improved the number of documents, the number of keywords, the number of unique words. When we talk about words, we are not just talking about individual words, but most of the time it's a combination of words, like in this case, selling price or time and materials. So those are engrams, chunks of conversation. There are algorithms to extract those, but they are either based on pre-existing engrams or they are character by character very slow. So we developed our own engramming system that is more efficient and is more generalized. So that seems to be a trivial problem, but if you do not apply the same engramming to all the components, meaning the creation of the room, the benchmark keywords, and incoming documents, you will never have a match. Then once we increase the number of keywords, we realize that keywords are not all created equal, meaning some of the keywords may have more relevance than others. So we work with the sponsor to have some help on giving different weights to the different keywords. Then there was the problem of determining the similarity between the words in the on the request and the keywords. So we initially used cosine similarity. Then we realized that this is averaging the results. We changed that. So that's basically after all the changes, we have 464 keywords, including synonyms. That's another important element. We expanded the corpus for the knowledge base to 537 documents for a total of 120,000 unique words. As I was mentioning, we developed our own engramming system. We assigned the weights. We used a different way to calculate the distance between, let's say, the incoming document, the request, and the keywords. And let me just share for a second. So that's the list of the keywords that we are using. So you have a Contratype. That's basically how we represent them in a shorter format. Those are the keywords. Those are the weights. So as I was mentioning before, it's 463 keywords with all the possible synonyms. Okay, so oops, let me go back here. Yeah, that's the joy of the Mac. So with the upgrades, that's the difference in the classification. So you have the previous approach, the new approach. With the new approach, there is way much more separation. You will get more on these charts. So this is a principal component analysis. There is a way to determine how much separated are the results of the classification. So initially, you have a bunch of elements that are kind of gathering all together in one area. With the new keywords, with the weights, with a bigger knowledge base, the separation is way much better. So we want separation because that means that the approach that we are using, the system that we are building, is able to better differentiate between the contract types. So the results, those are the different contract types represented by this fixed price or time material, whatever they are. The result is basically a table like this one, and I will show you the live system, how it works. So you have the document name, that is the name of the request, and then you have for each one of the contract types, the percentage of accuracy if you use that contract type for that particular request. And then the last column is basically the highest value. So you have this one that is 43 point something. That is the bigger value, the biggest value in the table, and the winner is FFP, and so on for the others. So that's basically what we have. The ability to discriminate between contract types was tested using PCA and using Monte Carlo simulation. And the results from the technical standpoint, then we are waiting for the contract officers to give us their feedback. That is obviously way much more relevant, but from the technical standpoint, we are pretty happy. Then we realized that the user may need not just individual documents, but may need the combination of documents for one single contract. So we differentiated the two parts. So the first use case was individual documents, meaning each request is treated as a separate document. So this can be done for training purposes or because in one specific case, that's the way it is. Then if the documents are concatenated, then the system is able to do the classification on the combination of all of those. Let me go now on the system. So one of the issues was, the system will look like this one. So there's a notebook with the system. So you cannot give something like that to contracting officers because they have no idea how to change. Somewhere there is a .pdf. So that's the file with the keywords. So if they want to change the keywords, they should go into this file. But you cannot really ask them to do that. So we created a user interface. That is what you have on your screen at this point. You basically, that's the clean version. So I wanted to have something already loaded, but we will do live the example. So you decide if it's a concatenated or individual files. So let's say it's an individual file. If it's concatenated, you will have the phrase here that will be changed. Then you upload. I preset some documents as an example. So just to give you an idea, that's the way they look. So that's one, that's the second. So those are the documents that we are analyzing. So let's say I have those two documents, open, this will go here, upload, they will be uploaded, and then I'm submitting. It will take a little bit of time. The reason for the time is because each time it's loading the room. Considering how big it is, it will take quite a while. For security purposes, each time you do a new request, will reset the memory. So meaning each time you have to load again the room, and this is why it's taking time. While it's working, we will go back here. It will take a minute or a minute and a half. So those are the results that you will get. So the results, just like in the chart that I presented before, it's the name of the document, the different contract types, and the one with the highest value, meaning this is the predicted contract type. And then you have a little bit of additional information. So this is a chart showing the differentiation between the different contract types, just to give you an idea of the level of separation, so how distant the different contract types are. And that's basically it. So let's see if the other one finished. Yes. So that exactly the same thing. When you do concatenated file, you basically take the files that are intended to be concatenated. So let's say those three, again, they will not look much different from the others, but those are files that the user can consider as concatenated, meaning related one to the other, and need to be examined or analyzed altogether. So I will submit that, it will run, and then we will go back to this one. So that's basically it. Let me go back here. Future developments, the current system is a proof of concept. So meaning has limitations, has not been tested on a larger scale, is not incorporating any feedback from the user, but it's working. So you saw that. We need to benchmark the results. So we may want to introduce a sort of after triage supervised system to refine the results, meaning forcing some specific cases, add a layer of reinforcement learning using the user feedback to as a score to maximize in the reinforcement learning, introducing external factors like the relevance of the request, previous agreements with given providers, competitiveness of the market segment, then expanding the user interface, and then eventually assisting, mentoring the users. So that's basically the end of my presentation. I just want to go back here. So those are the results for the individuals. Those are the concatenated. Obviously, there is just one line because all the three, whatever they were, files are considered as one. Just a final note, we have a website, NLP Lab, where you can find how we work, who we are. If you click on the hyperlinks, you will get more about us, how we work. So we have this approach that is based on components that we integrate. We have a couple of examples. So those are examples from WRT-1023, and you can see a little bit of the visualization. This is the risk analysis, risk decision support system. This is the technology monitoring system. So, and then you have a sandbox with some of the things we are working on. It's not been updated the last couple of months, but it's a sandbox. So in this case, our analysis of tweets related to coronavirus. And that's the end of the presentation. I really thank you for being with us, being with me for this almost 40 minutes. And if you have any question, I would be happy to address them.
Thank you very much for your talk, Doctor. We
Sure.
had a question that was addressed partially by the future work about how does the performance and the convergence to the preferred contractual vehicle scale with use, and maybe diving a bit deeper. You mentioned supervised learning, reinforcement learning. How do you see the performance of this kind of system progressing as maybe the data scales or the usage scales?
Great question. Thank you. Well, I mean, let's consider two aspects. So one, the performance in terms of response time. So the performance in terms of response time has not been optimized at all because it's a prototype. One of the things that we want to do is basically to upload the room once for all, and this will cut dramatically the waiting time. We are thinking about changing the way we extract those embeddings, those matrices, but that's another story. In terms of performance as accuracy in the classification, there are a couple of aspects. So the first one is pretty trivial. We are not completely sure that the keywords that we have are really covering the domain. So using the feedback from the contracting officers, we expect to expand the set of keywords, refine that aspect. The second will be to add layers. So one layer that I was mentioning before is to trace the feedback and use the feedback as a return channel somehow for the reinforcement learning, meaning adding a layer that at the very end will have an impact on weights that we can use in the classification. And then there are layers that are outside of the system. So I was mentioning, I was doing something similar for processing claims in the insurance industry. I use a system like this one for the first cut, but then there are rules and regulations in place that are very strict and you need to apply. So the system can clean up to a certain point, but then you have rules and regulation and you apply that. So we can use the same model, use the system for the triage, but then you apply hard rules that has been set, if any, by the contracting officers. The last portion will be external factors, like how critical is one request compared to another one. And based on that, how much coverage, how much, conservative will be one contract type compared to another one. So the combination of those two factors will add an additional layer, introducing another weight equivalent that will improve the performances.
Thank you very much. That's very, very thorough. Yes, a common theme in the natural language processing for system engineering is that it requires a fair bit of systems engineering.
Oh, yeah. Yeah, I mean, that's something that we are realizing more and more. But in general, in AI machine learning, I'm teaching a course on AI machine learning for systems and enterprises. And we realize that, one entire class is on system engineering. because machine learning is great, but it's not in a vacuum. It's part of a system and is actually a component with some peculiarities, but is part of a system. So definitely there are many other conditions that are outside of the technical aspects. Other questions?
Oh, we don't have any that have come in on the chat.
Okay.
If you click Q&A, you can find.
Yeah, we addressed that question.
That's the same thing. Okay, sorry.
Yeah, I mean, generally speaking, the more we will use the system, the more accurate is going to become. So that's a matter of fact. I mean, right now, even if we had a good interaction with the sponsor, but if you have more contracting officers working on it, each one will bring their experience, and this will help a lot.
We just had a question coming in about how do you think this might be able to adapt to other kinds of acquisition documentation, such as capability and needs documentation?
Well, I mean, if you look back at the slides, the approach is very reusable, meaning if you change the room, if you change the keywords, you basically can apply the same model to any domain. Obviously, you have the limitation on the representativeness of the knowledge base. That's not trivial, and you need to have the right keywords, but that's obvious. I mean, if you think for a second, if you stay just in the contracting business, if you are not an expert, you cannot do the classification. So, and that's a matter of fact. So we try actually to use the Google n million unique words data set for generating the embeddings. That was not very useful, because it's like asking me, what do you think is the best contract type for this request? I mean, now I can probably be a little bit informed, but generally speaking, I'm not an expert and I cannot address that. So the knowledge base, again, it's a knowledge-based system. If the knowledge is not represented in the proper way, it's not going to work. Then you can add refinements, but the core is the representativeness of the corpus that you use to generate the computational version of the knowledge base. We found this approach very interesting. So we initially used it for classifying emotions. So I was mentioning that in the presentation on 1010. And we use for classifying emotions the Plutchnik classification with a certain number of basic emotions. One of the emotions is joy. One of the shades of emotion of joy is ecstasy. But ecstasy is a shade of joy for someone else is a drug. So the same word in different contexts may have different meanings. So there are not many commercial analyzer of text that are considering one, the semantic metrics that you can get from text, and second, the context of the domain that you are considering. and the context, the knowledge base can change. So if you have a fixed ontology or a taxonomy, then you need to update each time things are changing. So in this case, you can automatically generate a new equivalent of taxonomy.
Professor, I think we are short of time.
Okay.
Sorry.
That's good. No, absolutely. I mean, I was just chatting. I'm sorry. Okay. Thank you. Thank you, everybody.
Thank you, everyone, for joining. Oh.